Hello, welcome back to Math 152. Today we are going to look at partial fractions again to clear up some of your misconceptions on this particular techniques. So we are going to start with the three example here, and then we are going to look at a slightly more complicated integral problems involving the use of this partial fractions technique. So if you remember, we use partial fractions when we have rational functions. Rational functions is a function consists of a division of two polynomial, a quotient of two polynomial. So as you can see here, we have a polynomial of degree 2, and here we actually have a polynomial of degree 4. And because we have the degree here is less than the degree here, so therefore we can decompose it like this. And remember that I said that if you have a quadratic terms, x squared plus 1. So what is on top of it should be a polynomial of degree 1 less than it. So in this case, you have a linear terms of the form ax plus b. So this is a linear terms, x minus 4, a polynomial of degree 1. So if that is the case, degree 1 less than it, you can think of it as if it is a constant. So you put a c here, and then same thing here, polynomial of degree 1. So here will be a constant. Now, this is true. This is true when you have terms that is not repeating. Repeating means that things that repeat means that things that looks like this. So when you have expression that is x to the power of 5, you would think of it as x. That is our base term, and then this is the terms that repeated 5 times. So when you do the decomposition using the repeating decomposition rule, so what you need to do is to write the repeating terms, which is the base terms here, x, and then you'll put an a, because your repeating terms here is x, is a linear terms. So on top of it should be just a number. So you have a over x, and then here you have b over x squared. So you just keep repeating the x from x to x squared to x cubed to x to the power 4 to x to the power 5. And when we look at the x to the power 5, so on and so forth, we are basically looking at the base terms, the repeating terms, the raised to the power 5, repeating terms raised to the power 4. So because the base term here, the terms that is actually repeating, is a polynomial of degree 1, so therefore here will be just a number. I'm saying this multiple times is because some of the students actually thought that we are still applying a rule like this here, meaning that when they see x squared, even though they are using the repeating decompositions, they are still wanted to write this as bx plus c. Now that's not true. Some of them see that this is x cubed, so they remember that we should write a polynomial of degree 1 less than it, so they will try to write these terms here as dx squared plus ex plus f. Now that is not true. So when you're using the decomposition rule involving the repeating terms, something that looks like that, your job is to identify what is the base terms that is actually repeating. So in this case, the base terms that is actually repeating is x. So everything on top of it should be just a constant. Then when you have this term that is not repeating, so the decomposition is the same as the one that you have before. So this is a quadratic terms, so on top of it should match with polynomial of degree 1. It's in the form of fx plus g. Now your repeating terms can be an expression that is not linear, that is not degree 1 polynomial. For example, if you look at this case right here, so if you want to use the repeating decomposition, so you have to look at the base case, like what is the terms that is actually repeating. And the terms that is actually repeating is x squared plus 1. Now, the repeating terms here is a quadratic terms. So on top of it should match with a polynomial of degree 1. So when you are repeating this, x squared plus 1 to x squared plus 1 square to x squared plus 1 bracket cube, the things that is on top of it has to be a quadratic term, has to be a linear terms, I'm sorry. So you're going to have ax plus b, cx plus d, ex plus f. Okay, and for this particular example, it also involves a term that is not a repeating terms. This is x minus 1. So again, this is linear, so on top of it should match with a polynomial. It should match with a constant. Okay, so try not to confuse this rule, okay, that govern this example with the rule involving repeating terms. Okay, so when you have repeating terms, you actually have to look at what is repeating, and then you will, based on that, decide what are the terms that is on the numerator. So the numerator, is it going to be just constant, or is it going to be a polynomial of degree 1? Will depends on your repeating terms. Okay, so let's look at this particular example here. So x squared minus 3x plus 7 over x squared minus 4x plus 6 bracket square. Now you have to be very careful about whether or not this terms here can be factor, can be further reduced to something that looks like this. And from high school, you know that that particular question is equivalent to looking at the discriminant b squared minus 4ac and see whether or not it is positive or it is negative. When it is negative, we know that there's no real roots, so therefore we cannot factor it like that, involving some real number here and some real number here. Okay, so because b squared minus 4ac for this term is actually negative, so we know that we cannot further reduce it into a factorization of this form. Now, because this is something that you really do need to check, because suppose I change the question a little bit, and now instead of looking at this, we are looking at this. So here you have x squared minus 4x plus 3. So this can be factored because x squared minus 4x plus 3 can be written as xx here, and then you will have a 3, you will have a 1. So it can be factored into x minus 3 multiply x minus 1. So the terms here looks like this, and because the square, so you have the square and the square here, so you kind of identify the repeating terms is x minus 3. And so this is polynomial of degree 1. So on top of it should match with a constant. So you are using the repeating rule, x minus 3 squared. So here constant. This is also a repeating terms, but it's a linear repeating terms. So here will be constants, and you have x minus 1 and x minus 1 bracket square. But if the things here, right here in this example, if this terms here is not going to be factorable, so your repeating terms now is not going to be linear. The things that you're going to repeat is actually this term, which is a quadratic term. This is a base term now. So because your base terms is like this, on top of it should match with a polynomial of degree 1. So your base terms that is actually repeating is x squared minus 4x plus 6. So because of that, the things that is on top has to be ax plus b, and here has to be cx plus d. Same thing though. So you cannot argue that this is a polynomial of degree 4. Therefore, here have to be like cx cubed plus dx squared plus ex plus f. No, we are not using that rule. Okay, so the procedure here involve repeating terms, and for repeating terms, this is how you should repeat it. This is how the partial fraction decompositions work. Okay. Now, also, don't forget though, before you ever split things up like this, you have to determine whether or not this is true by checking the degree of the polynomial and see whether or not it's in the pyramid shape. So as you can see right here, we have polynomial of degree 2, but here is polynomial of degree 4. So therefore, everything here that you do is legit. You can actually do a decomposition like that. Now, standard procedure dictated that we need to find A, B, C, and D. The way we do it is always cross multiply. So we cross multiply this term here across here. And as you can see, when you multiply this term here with and put it right here, that cancel. So you only have the cx plus d. And then when you put it here, one of the terms will cancel with the term on top. So you will have a surviving term, which is right here. So now, in order to find the A, B, C, and D, what you need to do is to compare the coefficient. Now, there are several ways you can do it. One of the methods, which is you can FOIL all this thing out, multiply all this thing out, and start to compare coefficients. Now, you can do that, and I will hope that when you're looking at this video, you should try to do it that way and compare it with my answers. But I'm a little bit lazy here, so I don't want to factor out all this thing, and we're going to check it by just by observing what should be the x to a cubic term, what should be the coefficient for the quadratic term, so on and so forth. And these techniques, you should also learn these techniques because sometimes you just don't want to multiply things out, because when you multiply things out and try to rearrange all that, it takes time, and sometimes you might make some silly mistakes. So, well, the second alternative method is just eyeballing it. For example, look at the highest power terms. Well, your highest power term is definitely not coming from here. It's going to be highest power term is going to comes from this expression here, and as you can see, the highest power term is actually a cube. So if you imagine that when you FOIL this thing, when you cross multiply, so you will have an a cube for sure, and that is the only way you can get a cube. You cannot get a cube from any other combinations. So your coefficients for a cube is a. So right here you will have x cubed and you will have a. But on the other side here, there's no a cubed terms. So you can think of it as 0x cubed plus that. So your a here must equal to 0. That's the reason why I said compare coefficients of x cubed, and then we obtained that this a here must be 0. Okay, it must be 0. Now we're going to do the same thing here, but now instead of x cubed, we're going to investigate how are we going to be able to get x squared. You cannot get x squared from here. There's no x squared. There's two ways you can get x squared. First is by taking this multiplied with this. That's how you get x squared. Another thing is you're taking these terms and multiply with this. That's another way you can get x squared. And you can see that that's the only two ways you can get x squared. Because when this thing multiply this, you do not have x squared. And when this thing multiply this, you do not have x squared. You do not have x squared here. So the only way you can get x squared is by taking ax multiplied the negative 4x, and also taking the b multiplied the x squared. So if you just concentrate on the coefficient, you will see that the coefficient for x squared here, right, is going to be negative 4a coming from this multiplication, and plus b coming from this multiplication, all right, coming from this multiplications. And so this is on the left-hand side, and on the right-hand side, your coefficient for x squared is 1. So they have to match. This gives you another equation, which is minus 4a plus b has to be equal to 1. Okay? Right. Let's try to do the same thing, but right now we are going to look at the coefficient for x. So how can we get x? Well, we get x from here. Okay? And can we get x from here also? The answer is yes. And also there's another way to get x, which is right here, which is c. So there are three different ways you can get x. So the coefficient for the x is going to be 6a. So you're going to have 6a. And then you are going to get x from here, which is minus 4b. And then you also have the c that's got left behind. So you have that. So this 6a minus 4b plus c will have to equal to negative 3. So this is how you get the third equations. And the last equations is going to come from the comparisons between the constant term. So obviously there's one constant term here on the left, and on the right, the only way, there are two ways you can actually get constant term. One of it is coming from this multiplications. Another one is just right here. So if you look at the constant terms on your right is going to be 6b and then plus d. So 6b plus d have to match with 7. So that's how you obtain these four equations. You have four unknown, a, b, c, d. You have four equations. Hopefully we can solve it easily and find the coefficients. And obviously a is already 0, so which means b is 1. That's easy. Substitute b equal to 1 here. You can, and also a is 0, you can get c immediately. And then once you have all that, put the b back in here, and you immediately found your d, which is 1, which means that the partial fraction decompositions give you this, right? So there is a is 0, so there's no x term. So you have a 1, and then here we do have an x term because b is 1. And then we also have, because based on the way we write this, so b is 1, c is 1, and d is 1. Okay, so that's the reason why we have this. Now, in terms of partial fraction decompositions, we are done, right? So that's the partial fraction decompositions. But we do partial fraction decompositions not to do it for fun. We do it because we want to integrate things that looks like this. Okay, so we decompose it. Okay, and then supposedly by decomposing it this way, we should be able to figure out this particular integral. So the next thing we want to do is figure out this integral. Okay, now this is going to be a little bit problematic, but we can do it. Okay, not a problem. So we are going to write all this thing, x here, 1 here, and 1 here. We're going to split them up like this. So this is coming from here. The reason why I am writing this from here The reason why I'm writing this form here as a complete square is because, as you have seen before, we will have to do a trig substitutions. So you better make sure that it's in the complete square. So we have that right here. And then here I'm taking the x and going to take this right here. And then I take the 1 and I'm going to decompose it like that right here. The x here will be like this right here. So we are basically just using the partial fraction and rewrite all this thing here into this expression. Okay, now we know how to deal with this. This is definitely a trig substitution. This is also a trig substitution, but it's a slightly more annoying one. And this is actually the u substitution. So if you plan ahead, and the only things that you have to worry about is actually if you want to use the u substitutions, I would think that it's easier to substitute the whole thing here as your u. So that's not a problem. Problem is the du. So the du is actually 2x minus 4, and we only have an x, so we can make 2x. But we also need to make a minus 4. So I am going to write this thing a little bit. There are many ways you can make, okay, so this is what we call the makeup method. There's many ways we can make up the 2 and the 4, but because I already know this is what I'm going to do, so I am going to make it a little bit neat, okay, a little bit easier for you to see why we are doing all these things. So right now, I am going to minus 2 and then plus 2 so that I don't change the whole thing. But then I just going to group this guy here and left it here. And then the 2, I'm going to kick the 2 out and combine this with 1 to get a 3. The reason why we can do that is because we have the same base. The denominator is the same, so we can so basically we're doing like a plus b over c equals to a over c plus b over c, this kind of stuff. So if I do a minus c plus c, if I do a plus 1 minus 1, I can move the plus 1s here, I can move the minus 1 to the other side because they all share the same common denominator. So that is the reason why I put a minus 2. You will see why we need the minus 2 in a minute. So I'm going to put plus 2. I'm going to move this thing and combine it with a 1 to make a 3. So I'm going to call this integral I1 because I don't want to do all these integrations in one shot. So it's complicated. So we want to split this into 3 different parts. So I'm going to integrate this and call the integral I1. We're going to integrate this separately and call this I2. I'm going to integrate this separately and call it I3. All right, so for the first terms here, we can do trig substitutions. So we are going to use this x minus 2 as our x, okay, as our x, right? So here, as you can see, the key thing is to be able to factor the 2 out. So you need to have a square root of 2 so that when you square it, you do have the 2. So the derivative dx is going to be like this. That's not going to be a problem. So we're going to put all of them together, and you can see why this substitution works with square root of 2, because once you square it and take that thing out, you will have this, and this whole thing is the secant square. On top is secant square, you have square root of 2 over 2, and this thing cancel, and you're basically integrating 1 dx, d theta. So this will give you theta. And so because of the substitution looks like this, you will see that your tangent theta is equals to x minus 2 over square root of 2. So therefore your theta is the arctangent of x over 2 minus square root of 2. So that's the reason why you have that, and this is nothing but the coefficient that you have right here. Now some of you know the formula, and you can kind of like immediately apply the formulas for this expressions. But I would say that no, not everyone remember the formula, and even if you think that you remember the formula, you might make mistake. So just follow the procedures on trig substitutions. You see this is plus, okay, so you have like u squared plus a squared, that kind of term, and you know that your u is definitely a tangent theta. That is going to be the things that's going to work. So you can still use the substitutions and get the answers like this. Okay, so that's your I1. Now I2 here, now you're going to see why I make this terms x minus 2, because as you remember, this is the u substitution, which I need 2x minus 4. So if this is x minus 2, I can multiply the entire thing here to get 2x minus 4. So the only thing I need to fix is to make sure that I also have the 1 over 2. So this is another alternative This is one of the makeup methods. You can make up all the terms as needed as you see fit. But right here, I'm using this so that it's a little bit neat, and it's slightly more easier to understand. Okay, so once you have this whole thing is just nothing but this integral, and therefore you will get this answer. So that's not a big deal. The big deal is basically like the splitting part here, that once you have to make this right, everything else is going to be pretty easy. Now, the third terms is going to be this. Okay, the third terms is actually right here. As you can see, this is our third term, I3. And I am going to do use the completing a square methods to try to complete the square of these expressions. And that's what I got, right? So that is a square. That's something different from the first I1, is that we have a square right here. But the substitution methods, the trig substitution methods will still work. And if you put everything back in here, you will see that you have this, and then the cancellations give this, and this is cosine square. And by now you should be very, very familiar with how to deal with cosine square. You use the double angle formulas, and you change it to something that is integrable. So things that you know how to integrate, and integrating one gives you theta, integrating this gives you this. And then the one last thing is you want to write it in terms of the x. So again, remember that we only have theta, we doesn't have two theta, so we have to split it up to sine theta and cosine theta. And using this triangle, I'm pretty sure you know how to construct this triangle now because we know tangent theta. So tangent theta is from here. You can see our tangent theta is x over 2 over square root of 2. So x minus 2 over square root of 2. And the Pythagoras identity theorems give you the length of this side. And then you can just substitute. So this is theta, so theta equal to that. And then sine theta is going to be this over this. Cosine theta is going to be this over this. And then you multiply all, this is the same term with square root, so you multiply them up. Also distribute all this thing in, you will see that this is how you get I3. So this one is a slightly more involved, question that's slightly more involved, because we do have to split into three different integral and take care of all these integrals separately. So the final answer will be putting in your I1 and your I2 and your I3. And even though you have all these constants will be absorbed into one single big constant, and that will be your answers. Okay, so one quick question is going to be like, are we going to see all this kind of question in the exam? Now, no, in the exam, we are definitely not going to ask you to do a question that is so complicated, because each of them require a lot of work. So, but for homework, it's a fair game, right? Because you do have time. You can come to office hour. You can go to your SI. You can work with friends. So that is not going to be a problem if this is set as a homework problem, but this is never going to be an exam problem. Okay, so hope this thing helps to clear up your misconceptions, especially on the decomposition part. All right, so that's it. I will see you on Wednesday.